The final exam and the review from which the final is derived is also derived from American Chemical Society exam that I got hold of from 2010. So this is the type of exam you would get if you were going into chemistry, and they were going to actually, if I know the former chemistry professor from Concord, and he used exclusively final exams were from ACS because his students were headed that direction toward chemistry degrees, and he wanted to be able to compare them across country. But I got to looking at it, and they're pretty good questions. So I said, all right, I'll use them. So let's take them one at a time until we are 6. Which salt will form a neutral aqueous solution? Remember the rules of thumb for solutions formed from a salt. If the salt, let's see, if we use just a generic like that, acid base forms a salt like cation first and water. So if you just put this into solution, what's the pH going to be? Is it going to be acid, neutral, or basic? The rule of thumb is if this is a strong base and this is a strong acid, then this is going to be neutral. Okay, so if your cation and your anion are both derived from strong acid base, then your aqueous solution is going to be neutral. So the only one that fits that one is A, KBr, like hydrobromic acid and potassium hydroxide, both strong. Now, if while we're on the topic, if say this is a weak acid, right? And you take the salt from that combination, you're going to get a basic solution. Okay. And vice versa. If this is weak and that's strong, then you're going to get an acidic solution. If they're both weak, then you have to compare the Kas and the Kbs. If they're both weak, like that, and this one has a Ka and this one has a Kb, whichever one is bigger tells you which one is going to be. So if Kb is larger than Ka, then you're going to have a basic solution from the salt. All right. Number 2, which conjugate acid-base pair is not correctly matched? Remember what we have to have for a conjugate acid-base pair. Think way back in the dim reaches of your mind. When you have an acid, say, let's take phosphate, like phosphoric acid. Right, remember, dissociations, proton dissociations occur one at a time. So the acid-base pair for this one would be 2 hydrogens. And then we lost a positive, so that means we have a negative left over. Right. Then you could take this one. Well, let's just say you could take that one and then go to this. You could take this one as an acid, and then you go to its base, conjugate base there. So that's an acid-base pair. This is an acid-base pair, and this is an acid-base pair. Any other combination is not valid. So to answer that question, which conjugate acid-base pair is not correctly matched? Well, the other thing that you have to have is this part of the molecule has to be the same. So we're good here. HBr and Br minus. Yep, you lose one proton. That one's good. HNO3 and NO3 minus for B. Yep, that one's good. How about H2O and H2O2? Well, I don't think so. First of all, it didn't lose a proton. And second of all, this part of the molecule is not the same. So that's your bad one. And the last one is correct. Sulfuric acid and hydrogen sulfate are a conjugate acid-base pair. I like that sound. You need it bad.
We had straight line winds last night and it laid our corn down. It
Oh,
was bad. Like it was like a good 70-mile-an-hour wind.
Well, he'll stand back up, but it'll be like this.
Yeah, well, he went back out and tried to stand it up, but it was flattened.
Yeah,
That wind was pretty bad.
that's unfortunate.
Yeah, and then it barely rained.
Okay, number 3. According to the Lewis theory, a Lewis base is what? This is just definitional. A Lewis base is electron pair what? Donor. Right? A Lewis acid then would be an electron pair acceptor. Okay. There's no logic there, you just have to memorize it. And we could go in through some sort of a logic. We could draw a comparison between Bronsted-Lowry acid base and Lewis acid base, show how the electrons move there, but it's probably easier at this point just to memorize it if you don't already know it. Number 4. When equal molar amounts of these sets of compounds are mixed in aqueous solution, which one will form a buffer? Okay, if you're going to have a buffer, that's the best combination is equal molar amounts of the acid and its conjugate base. So you need for the Anderson-Hasselbalch equation. You need your acid and your conjugate base in equal amounts. And if they're in equal amounts, that means this term goes to 0 and the pH is equal to the pKa. Y'all remember that from our labs. Okay, so we have to have a conjugate acid-base pair. Right? So sodium hydroxide and sodium carbonate. No. Right. Sodium hydroxide is a base. Sodium carbonate's not conjugate, does not produce in the anion form. That's what you look at. Sodium hydroxide. So what would be well, that doesn't work. You got 2 bases there. A is not going to work. Sodium carbonate, sodium hydroxide are both bases. Hydrochloric acid and sodium hydroxide. Strong acid, strong base, you're going to get a neutral solution no matter what you do. Right? Okay. How about hydrochloric acid and sodium chloride? The condition there is that hydrochloric acid is not a weak acid. You have to have a weak acid or a weak base, but most of the time we discuss it in terms of weak acid and its conjugate base. So you do have an acid and its conjugate base. You have the HCl and then you have the Cl minus, right? So that's a conjugate acid-base pair, but that's not weak. If it's not weak, buffer's not going to work. Has to be weak. So acetic acid and the acetate ion, D, that will work. That will give you a buffer. All right, number 5. Which titration has an equivalence point with a basic pH? Okay. Where are you at the equivalence point? Where the acid equals the base, molar equivalence. Right? So you can go back to our first question where you're trying to determine the pH of a solution. And you look at the salt, you look at where the cation came from, where the anion came from. And if the cation came from a strong base and the anion came from a weak acid, then your solution is going to be basic. And that point is where you have those molar equivalents of the two. So when you have the molar equivalence of the acid and the base, that goes back to question 1. Right? If we titrate acetic acid and sodium hydroxide, where is your equivalence going to occur? Basic, because sodium hydroxide is basic. Okay. So if we're looking for a basic pH, I'd go to D. Right? Acetic acid and sodium hydroxide. Now, if we just look at the others, C is a strong acid and a strong base. That's going to be neutral. B is a strong acid and strong base, neutral. A is a strong acid and a strong base, neutral. A, B, C, they're all neutral. All right. So your best answer is D. If you want a basic pH at the equivalence point, you need a weak acid and a strong base. Let's say 6. Identify and justify the Bronsted-Lowry base in the reaction. All right, let's see. We have this ammonia plus HBr, right? Yeah. Strong acid is going to produce ammonium, and well, they don't separate. You just say this. Okay. So, way. There we go. Bronsted-Lowry base in the reaction. Which one donates the proton? Which one accepts the proton? This one accepts the proton. It's the base, correct? Yeah, this is the base. This is the acid. And that's it. That's the base because it accepts the proton. So D is the answer. All right. Seven. Which two elements form a compound with a stoichiometry XY? If you're going to have a stoichiometry of XY, that means one cation, one anion, and they have to be opposite charges but equal in magnitude because you only got one of each. So it could be a plus, it could be it could be a plus minus, it could be a 2 plus and a 2 minus, it could be a 3 plus and a 3 minus. As long as they're equal. So you look at your choices, aluminum and chlorine. Aluminum forms a 3 plus ion. Chlorine forms a 1 minus. That's not going to work. How about aluminum and oxygen? Well, that's a 2 minus. That's not going to work either. How about magnesium? Right? Alkaline earth, 2 plus, and sulfur, 2 minus. There you go. That'll work. And then the last one, of course, won't work because sodium is +1 and oxygen's 2 minus. Okay, so you look at the charge balance. So if I switch that around and said X2Y, right, then X would have to be a +1 and Y would have to be a -2, for instance. That would be D, right? What would that compound look like? Sodium, like that, sodium oxide. So actually going back to naming conventions. Type 1 compounds. in this case. All right, let's see, 8. Oh. Let's see, I might have to, let me shrink that a little bit so we can see it all. My goodness, it's gonna get so small we can't see the writing. Okay, let's get the question first and then we'll look at the pictures. The reaction, HNC gas yields what? HCN gas. Go. Let's see, the reaction is 0 order in HNC. So 0 order. We're talking kinetics here. Which plot is correct for this reaction? If we plot this concentration versus time, right? What kind of plot are we going to get if it's 0 order? We're going to get a straight line plot, aren't we? If we just plot this against that, then we should get a straight line plot, concentration of HNC. We should get a straight line plot. So that's A. What if it were first order? Natural log, right? What if it were second order? Like that, right? Like the inverse, plot against time. All right. Number 9. Okay, number 9. What is primary attraction when gaseous HF condenses? We're talking about the forces that cause it to condense. So these are intermolecular forces, right? So HF is what? That is a very polar compound, right? So the forces, now we've got dipoles there, we've got a dipole. So it interacting with its neighbors, we're going to get a dipole-dipole interaction. That's the primary force. What would be a secondary force? The one that's always there.
The one dispersion?
Mm-hmm. Yeah. It's not very useful because it's so weak. This is so strong, then this one, we can ignore it. But it's a secondary consideration. But it's not just dipole. If you have the choice, which we do here, remember, you have the opportunity for hydrogen bonding, which is a dipole-dipole interaction, but it's the strongest of that category. So if that one's missing from the selection, pick dipole-dipole. But if hydrogen bonding's there, definitely. Right. If hydrogen is connected with fluorine, nitrogen, or oxygen, these could have something else over there. Then you've got the potential for hydrogen bonding. All right. Oh, so the answer is D. Need to be made bigger. Let's see, number 10. Which weak acid yields a buffer solution closest to 9.3 pH? So we want a buffer at 9.3 pH. Well, 9.3 is going to be equal to pKa plus the log of the conjugate base divided by acid. And we're only concerned with this comparison here because if it's a buffer, we're going to say those are equal and that term just goes away. So we're looking at a comparison here. So which one has a pKa that's close to 9.3? Well, we're only given Kas. So we'd have to calculate the pKa for each one. Or we could, I'll tell you what, why don't we just convert this one into Ka and then we could compare it directly with the rest of them. Yeah. So if this is we want a pKa that's close to that. So if that's equal to 9.3, then Ka is equal to what? 10 to the minus 9.3, right? 9.3, change the sign and then do 10 to the power. So I get 5.01 times 10 to the minus 10. So which one's close to that? 10 to the minus 10 looks like boric acid would be the closest one. Keep me honest.
Yeah.
All right. Let's see, 11. The pH of a 0.01 molar solution of weak acid is 3.76. So let's see, concentration of weak acid is 0.010, 0.010 molar. And the pH of that solution equals 3.76. Okay. What's the percent ionization for this one? Well, remember our definition for percent ionization. Percent ionization of an acid is equal to the concentration of the how much of the acid was converted, right? So we need this part divided by this part, the original amount, times 100, right? So we're given the weak acid as this. It's only got one proton. So if we find out what the concentration of the protons are, we also know the concentration of the conjugate base, correct? Because it would decompose into this plus this. So if we know this one, we can find that one. They're equal, right? We got the pH, so we can find out what the H plus is, right? 10 to the minus 3.76. So to change the sign, do this to it. Oh, I need some more decimal points. Display. There we go. So I get 1.74 times 10. Well, let's see. The number of decimals is a significant figures. So it's 1.7 times 10 to the minus 4. Molar. There we go. So we got 1.7 times 10 to the minus 4 molar here. Times 10 to the minus 4. Oops, about 14. There we go. What does that leave here? Well, 1, 0, 0 times 10 to the minus 2. minus 1.74 times 10 to the minus 4. Because that's how much we used of it. Times 100. So let me see. 1 minus that subtract. So I get 9.8 times 10 to the minus 3. Okay. For this term right here. And we'll divide that into this one. Divide times 100. So I get 1.7%. So what you got?
I'm gonna give you something.
Okay.
It's not what I. I think anybody.
Leave out a parentheses. Need to convert the world over to reverse Polish notation.
Well.
That's a
Yes.
tall.
That's
Yeah.
what I get.
You get that? Okay. Yeah, I know it's a tall order. I mean, when videotapes were out, Betamax was better picture and sound quality than VHS. But VHS had a market force that was irresistible.
I got it now.
So Sony's Betamax went out.
I noticed like on TVs that have like this CD and the VHS like duo, the VHSs are a lot louder than the CDs.
Mm,
Like on the duo TVs, I don't know if you've noticed that before.
No,
Yeah,
I hadn't noticed that.
or maybe it was just Cinderella that was louder, I don't know.
Talking about volume. I know this is true. When you've got you're watching a TV program and a commercial comes on, commercials always 10 decibels higher,
Oh,
louder.
really?
You never notice that? Yeah.
Well, I mean, it seems like they're louder, but I mean, I don't really pay attention.
Yeah. Oh, they're louder. It's a marketing ploy.
Yeah.
Yeah. Well, I've always known this. Advertising is just legal lying.
Everything's schemy anymore.
Okay. We got a few more minutes. Let's try another one. And then we'll pick it up next Tuesday. Which sketch best represents the titration of a weak monoprotic acid with a strong base? Right? If you got a weak base and you're going to titrate it with a weak acid, you're going to titrate it with a base. And you got this scale here, and you're adding the base here. And you got the pH here. Where are you going to start with a weak acid?
Well,
Yeah, low pH, right down here somewhere. It depends. And so it's going to gradually increase. Actually, it increases pretty quick. When you first add the base, it increases quick, and then it flattens out. And that's your buffer zone. And then you get toward the equivalence point here, and then it keeps going like that. That's if there's only one proton, right? If it's a monoprotic base acid, that's what you'll get. So B would be the best answer there.
so what would A be?
A would be diprotic. Actually, that's not a good drawing. I guess it's okay. So you get your first proton would come off here, and you'd get an equivalence for that first proton. And then the second proton would come off and give you a buffer at a different pH. And then it reaches its second equivalence, like that. So you have a potential for a buffer here and a buffer here. you have the first proton equivalents here and the second proton equivalents there. So if you're titrating a base against sulfuric acid, then, and you want to know exactly how much sulfuric acid is there, you're probably going to go to this one. That's your equivalence point for sulfuric acid. And if it was phosphoric acid, then you'd have three of these, three steps. This would go back up again like that. That'd be another one for phosphoric acid. Okay. I guess we can stop it there and let me make a note where we left off.